Okay, good morning everyone. So finally we move to the last topic will be discussed in this class, which is electrostatic discharge. In general, we call this as ESD issues. So ESD is also one of the main concerns related to reliability, not only in the device level, but also in the circuit level and system level as well. So, and also it's getting more and more important once we move to technology beyond the certain node, especially also related to the scaling. We also see the ESD challenges getting more and more important. So in here, in this lecture, we still will review the basic related to the electrostatic discharge, ESD issue, what the fundamental reason that will cause the ESD degradation, and what would be the possible prevention that allow us to avoid the ESD issues. So here is the first is outline. For sure, first we will introduce ESD. So what ESD means to us, why the reason will cause the ESD issue. And the second part, we will talk about the fundamental reason leading to the current shooting for the ESD is mainly related to the parasitic. We have the parasitic NPNP in our transistor. So which is the parasitic NPNP is a combination of, we have the NPN junction, also the PNP junction, or PNP parasitic BJT that can exist in our typical CMOS. So in the typical CMOS, as you may know, the CMOS is a combination of the NMOS and PMOS. And inside the NMOS and PMOS, we will have lots of the parasitic junction, and this parasitic junction in the end will cause the NPN or PNP parasitic BJT that can cause latch-up issues. So this will cause the current has such characteristic. This is typical IDVD characteristic. And once we has increase the drain voltage to a certain voltage, and there's a moment that will trigger this parasitic NPNP. In general, we call this NPNP, which also as in ESD we consider this is a parasitic transistor, but in other domain, like for the power semiconductor, actually we have another name for this NPNP that we call as a silicon control rectifier. We just also call this as a SCR. So once there is a huge drain or huge voltage suddenly applied to our transistor, and at a certain moment, this large drain voltage will start to trigger this silicon control rectifier. And once this silicon control rectifier is being triggered, is being turned on, then we start to see there's a huge current increase, like in this way. This is what we call as a snapback. So this snapback, as you see, this is snapback is a very high current, and also in the meantime we have the very huge voltage applied so it can cause a huge damage in our device. Sometimes also related to the thermal damage, because in this moment we have a huge power existing in our transistor. So in this chapter we will try to understand why there's a latch up, or sometimes we call the snapback issues here. And also we will talk about how we can qualify our product as being for a certain ESD standard. So once you send out your products to your customer, definitely you need to make sure for reach to the certain standard, and make sure that can be immune from the ESD reliability. So then we need to standardize the ESD models and also the standards, so that can give us a customer to understand that the quality of our product, that can avoid the ESD issues. And also we will talk about the typical ESD testing methods. Usually we use a way we call the transmission line pulse. That's what we call the TLP. So this is a TLP, is also very widely used for no matter for the on-wafer or package level. We use the TLP to look at the reliability, especially related to the ESD issues. And also in here we will talk about some basic ESD protection strategy, and also the future challenges of the ESD. So we will talk about what happens if we try to, for example, move from the planar device to the FinFET, and what would be that influence in our ESD issues here. And just one, because ESD is a pretty broad topic that is in terms of from the device level, circuit level, and also system level, and also many different devices has their own really unique ESD reasons. If you look at for silicon, if you look at for 3.5, they all suffer the ESD, but the fundamental reasons might a little bit different. So in here, in this class, because we only take one class to explain the ESD, so we only focus on basics of ESD. And the origin of ESD in the device level. But I believe the basic understanding from the ESD from the device level is already enough to provide us everyone the basic understanding if you are going to face the ESG challenge in the issue. Because if you look at the circuit level or even the system level, actually they try to address the issues always coming from the fundamental from the device level, because the device level is a fundamental bottleneck. Even you put the circuit level, try to prevent ESD or system level, in the end it's always we want to address the challenge inside the device level. So I believe that understanding device level can be always key, even for the circuit and system considerations. Okay, so first, just introductions. What is exactly the electrodischarge? Actually, this electrodischarge is pretty like the nature phenomenon that you have been already observed, especially in the some timing where we have very dry, especially like in the winter time, or sometimes in the western country, in the very high altitude region. Usually the air is very dry. In Taiwan, the air is pretty humid, so you won't you won't observe this very often, but once we're getting close to the winter time, you will start to feel like once you touch the certain metal, even your computer, you will be discharged. Once you're being discharged, that means you will feel like the electrical shock between your fingertip and some insulator material, some like metal material. For example, the computer can be also one of the things that you will feel there's a discharge happening. So what I'm talking about discharge is related to these things. So this is an illustration that the reason why your fingertips and this is kind, for example, like PCB board or whatever for the circuit or the computer that you have discharge is because of you have the charge in your fingertip, and you have on the other hand, the PCB can be grounded. So at that moment, you start to experience a certain charge flow from your fingertip to your PCB board or your circuit board, your semiconductor device. That can cause a discharge. So this discharge event is mainly due to the triple electrically generated charge. So what's a triple electrically? So that's just because you try to touch another material, and then the charge on your hand is flow into another material that cause the charge flow. So in Mandarin, the triple electrically is called 摩擦放电. So at that, regarding for this phenomenon, it can have the very high current and very short durations. Usually it's happening below probably around like 100 nanosecond. And also it can cause a stress event up to kilovolt. So this very high current, short duration, and very extremely high voltage that cause this is one of the major reliability threats for our ICs, because it's cause over voltage and also the overcurrent stress in our IC. So that causes very severe damages here, and this is become one of the reliability and yield problem. So if you start to look at, so if you already have a chance to start to test your own chip, to test or even the commercial product, sometimes you might have the feeling that the device, even you haven't started to really do some test yet, but the device probably is failed. And one of the reasons the device already failed before your testing can be also related to ESD issue, because your hands actually touch on those ICs that can already cause ESD issues. So in general, ESD is a current event that complete under the less than 200 nanosecond. And also the rising time can be the order between the picosecond and nanosecond. So ideally it's a very fast event. And we sometimes also call this as an electrostatic overstress, or ESD, has been as a predominant value cause across all products for all technology in many companies here. So this is another illustration that because your hands has some charge, and also once you touch your IC, you can cause the triple electric phenomena, and that will cause the discharging. So this charge discharging is the issue that we are talking about here. It's the ESD issues here. So ESD problem can be in generally avoided by first one, we do some preventions. We try to do something to avoid the build-up of the static charges. And second part is protection. So we will try to place the certain protection circuit on chip to protect the ESD issues. So idea for this circuit is because as you already know, the ESD event can cause a high current, high voltage. So we want to have a certain protection circuit that can make sure that this high current can be flow away without being inside into our core IC technology. So we design this protection circuit that this high current can flow away and without entering into the IC that provides the functions. And the evaluations of new technology make the design of the proper protection very, very challenging. So we will also talk about this later. So here is a typical, the ESD cover the very large IV range here. So this is example. For example, in our typical CMOS, what our operation current might be 0.1 amp, and our operation voltage might be below 2.5 volt. But once the ESD event is happening, our CMOS chip can be suffer for few thousand volts and few hundred amp. So now you can realize that definitely our chip cannot sustain such high current and high voltage. So definitely it will cause huge damage. So basically our device is definitely completely failures under the ESD event. So that's a pretty challenging issues. So we need to do something to avoid this happening. So if we look at for the fundamental of ESD, so the idea is pretty simple. As we know that the charge can accumulate in any material, just we shown here, the charge Q is equal to C times V. It depends on what kind of material that can cause a different the charge here. And so this is an example. If we have a two metal plate, one metal plate is here, another metal plate is here, and as long as these two metal plates separate with a certain distance, so we can form the capacitance here. So this is the reason that we can have the charge accumulated in any material. And the charge induced depends on the position of material in the triple electric series. And this is something that we already face in our typical lifetime here. So any material can accumulate excessive number of the charge during the friction and subsequent separation. So once we try to have the friction on one material and then later on we separate, actually we start to have the accumulate these additional charges here. This is because due to the transfer of electron from the atoms at the interface here. So this is pretty like I think we all already know this from the junior school, from high school, already know that the friction and the suppression will cause a triple electricity. And this phenomenon is really depends on the different RH. So what's RH? This is a relative humidity. So now you can see if you are in the environment with a relative high humidity, so this is ESD voltage So that will be around this range. But if you are in the relatively dry environment, then the voltage is highly increased. So that's why that you will feel this discharge in the very dry region, especially related to the winter time. So the amount of charge generated through any typical process involving friction and separation strongly depends on the materials involved, and also relative humidity, and also the texture of the material surface and speed of the separation and area of a contact. So in anyhow, the charge generated, it depends on lots of factors, but it highly depends on materials, our humidity, the texture, the speed of separation, and area of contact. I think these are pretty fits our living experience in the daily life here. And an ESD event, usually below 3000 volt, will not be detected by human being. And therefore, in a 3000 volt ESD pulse, the current content is typically about 2 amp or more. And the static electricity, such as is harmless, since it's likely to remain at a state until acted upon by external electric field or force. So here is some more like the pretty fundamentals related to the triple electricity here. So as we all know that this is highly depends on the different material. So we can see this is a more positive more positive charge in this material and more negative in this material. So this can cause a different triple electricity event. Now we look at what would be possible, the ESD, the value that can be induced by the ESD. So this is the ESD induced values here. So as we already show that once the latch up is happening, this is our IDVD curve, and if we suddenly our transistor suffer for the very high electrostatic stress, so that means suddenly the very high bias is applied in our transistor, and this high bias is mainly due to the ESD event. So this is due to the ESD event. And this ESD event will trigger the SCR. That's where we have been previously briefly talked about. So at this moment, the SCR can trigger. And this will make our CMOS reach into the latch up. So once the transistor is being in the latch up, that means we start to see the high current is happening. So this is event where we have been explained previously. This is what we call the snapback. So the issue is always happening once we have such high current here. So this high transient current can cause thermal damage. can cause thermal damages here. So that's the second part, thermal damage. So this thermal damage is due to very high transient current generated by ESD pulses, and so therefore we can see this is a certain issue that we can see. We have a certain, this is the metal pad in the drain and source, and this is the thermal damage in the metal pad. It's kind of like the melting. So that's the thermal melting issues in the metal pad. And of course, because we have such high bias, ESD pulses immediately happen. This can also cause dielectric failures. This is due to the high electric field induced dielectric breakdown. So this can also cause dielectric failures. So then we cause a breakdown of the gate oxide here. So now you can see that this is the last topic we cover, but in anyhow you will find out that the gate dielectric is always the most weak part in our semiconductor transistor. No matter if you consider the first one, we talk about the bias temperature and stability. This is related to trapping happening in the dielectric or interface. Or second part is related to the TDDB. That's also related to our dielectric reliability. But also for ESD is the same. Dielectric is also one of the weakest part that can lead to the huge ESD-induced failures here. So therefore, lots of the ESD protection we will see later on is mainly try to do some additional small circuit to avoid the ESD-induced damage in our dielectrics. And this is some additional pictures for your reference. So this is gate oxide damage, this is metal melting damage, and also we have an interface damage. So in anyhow, the ESD can cause shorting, burnout, heat damage, interface damage, and leakage current. So it's the issue can cause the several big issues in our in our chips, in our transistors. So now we have start to look at a little bit more at what is exactly the SCR, and why we will have the parasitic PNP or parasitic BJT in our traditional CMOS. So here is a schematic. So the latch up in the CMOS is basically we have the unwanted SCR due to the parasitic transistor. So as I say, SCR is a transistor that combines with a PNPN. For power semiconductor device, actually we intentionally to fabricate SCR for a certain AC to AC rectification application. But in the CMOS, actually we don't want SCR because that causes these latch-up issues here. So here is a typical CMOS. As you already know, the CMOS is a circuit that combine with two different type of a transistor. In the bottom is N MOSFET. In the top is P MOSFET, and we have the V in and also V out here. So that's we generally consider as a CMOS. And CMOS is the main the blocking the main block for the logic circuit. So that's have the function to convert the digital signal from 0 to 1 or 1 to 0. So that's why the CMOS is very important. But unfortunately, inside the CMOS, you found out that the structure, although in terms of circuit level, it's very simple. This is very simple circuit level. But if you look at the full device schematic, this is a full device schematic here. So in here we have this one, we have the P-type substrate, and then we have the source drain. So this is the N MOSFET. So we have NMOS. This is something that we have been discussed for a while. For the every basic transistor, we only mainly talk about this part. And of course, on the other hand, we have this part, which is a PMOS. This is the most two important part to realize the CMOS. But unfortunately, you can find out that because in the CMOS we have the many PN junction. For example, we have the NP. This is a P-type substrate. This one is a P-type substrate. So we have a PN junction here, and also this PN junction will lead into this one, connect to this one. So therefore, if you look at carefully, you found out that there's a parasitic BJT happening here. On the other hand, we also have another parasitic BJT happening here. So inside the typical CMOS FET, we have the parasitic cross-coupled BJT to form a silicon control rectifier. So that's why inside our CMOS, what we have not only the typical N MOSFET, P MOSFET, we have many PN junction, and this PN junction can form the parasitic BJT, in the end become as a silicon control rectifier that can cause as a huge current latch-up happening. So now, if we put that equilibrium circuit for the latch-up, so we have this NP structure. So this is what we call the silicon control rectifier here, and this is our supply voltage VDD. So if the latch-up is happening, so once this is happening for the latch-up, and this will cause the high current between VDD and VSS, which is this one. The high current between VDD and VSS, so that will cause a low impedance path between the power supply here. So that's an issue we will have once the latch-up event is happening. So the next one is we start to go back to the fundamental. We need to understand the operation of the silicon control rectifier, because the main issues inside the ESD for the CMOS is mainly due to the unwanted SCR. So the next step is we need to understand how SCR operations. So now I took the slide from the power semiconductor device courses. So as I already said, in the power semiconductor device, we actually intentionally to fabricate the SCR. But in the power semiconductor device, we don't call this as a SCR, we call this as a thyristor. So this is a structure for the thyristor. So thyristor is a structure that combines with NP. And this is also structure with only two terminals, which is cathode and anode as well. So for the power device application, the SCR provides both forward and reverse voltage blocking capability. That's very suitable for the AC power application. So in here, we won't talk too much that how this apply to the AC power, but this is just give you an idea that this PN-PN junction sometimes it's bad if you look at for the ESD event, but sometimes important if we put it in another application. If you look at the thyristor, you put it in the Google, you'll find that the thyristor is a transistor, one transistor, probably huge like this one. This is just a one thyristor, and usually it's happening in the electrical transformation, especially in the some of the electrical station. You will see that there's a lot of the thyristors mainly help us to do the AC power application. So if we look at for this NP structure, we can also consider the equilibrium circuit like in this way. So we have the one side is a PNP, another side is NPN, and can be also illustrated by this circuit schematics. So now we will use this circuit schematic to understand the working principle. So in here is there are lots of text here, but just don't worry that the text is just for easy for you to review later. But in here we will just mainly use this circuit schematic to understand the working principle. So the first of all, in the typical thyristor or SCR, actually we will intentionally provide a gate current to trigger the device. So then you can see there's a gate current in here to trigger the device, and also this one to trigger the device into the on state. And the gate current will forward the bias of this junction J3. So this gate current will forward the bias of this one, and therefore to initiate the injection of electron, and the inject electrons trigger a positive feedback mechanism. Provided by two coupled bipolar transistor within the SCR transistor. So the first state is we have the gate triggering current, and the gate triggering current will start to forward bias this junction J3, will forward bias this J3, and therefore we will start to have this gate current will flow to this region. If you are familiar with the BJT, so the BJT is the current drive transistor, the MOSFET is the voltage drive. So we have this base current will start to trigger this NPN, and once this NPN is turned on, we start to see this NPN has a current flow in this way. right? So this is because of our NPN is turned on. So once our NPN is turned on, the NPN BJT will start to deliver the current, and the current is flow in this direction. And this current becomes the trigger current of this PNP. So this current is become the base current for this PNP. And therefore we can foresee this PNP will turn on again. So once this turn on, this becomes another contribution here. And then this becomes a loop. Why it becomes a loop? Because this current supply again into the base of this ampere. So now you can foresee this is kind of like the closed loop and generate the current by itself and then cannot be stopped because there's no way unless you have to do some additional. Otherwise, the current, first we give it a gate current and then this current will become the base current to trigger this one. And once this turns on, this will start to have the current 3. And this current 3 will become the base current of this one. And that will turn on this PNP again. So we have the current 4. And the current 4 will come back to supply as a base current of this ampere. So this is the positive feedback mechanism. So the first bipolar transistor, NPN, the first bipolar is an NPN transistor and formed between the N cathode, P base, N drift region, and second bipolar is a PNP. This is something we have been shown in the schematic here. And the issue is that we start to see there's a chance to form these regenerative actions. So regenerative action is exactly the phenomenon that we explain here. So once the current flow is initiated through the transistor, they can provide the base driving current for each other. So once this ampere is turned on, this ampere provides the base current for this one. So this will turn on again. And this turn on again, this current provides the base current for the other one. So this is how we call as a regenerative actions. And this is because of due to the provide the base driving current where we have seen here for 2 and 3 for each other. And you can see this is a closed loop, and then the transistor can operate itself without any further bias because they can sustain by their base driving current. So in this process, the collect current of NPN provides the base driving current. So this is what this is talking about. The collect current of NPN provides the base driving current for PNP. And then the collect current for PNP provides the base driving current for the NPN. So these regenerative actions allow the stable operational device into on-state without any additional gate driving current. So that's why we start to see this So if you look at back for the issue where we have been seeing in our ESD, so once we have very high ESD pulses at the one moment, if we suddenly trigger this SCR and we start to see the current shooting. This current shooting is due to these regenerative actions. This causes the issue that we call the latch-up event. So now, if we look back again to the typical CMOS ICs, okay, so now if you look back for the latch out in the CMOS IC, so as we already explained in the previous slide, I think so far for you, you should be able to a little bit get familiar with why this circuit can cause a huge current here. So this is because we have this parasitic BJT here. So once the PNPN device is triggered, the latch-up event will start, and the ESD event might trigger the latch-up in the CMOS. And the reason why the current can be keep increasing is because, as you already know, in the BJT, the current is dependent on the current gap. That's what we call the beta. And most of the case, the beta is always larger than 1. So therefore, the gain of this PNPN is a beta 1 times beta 2, which is larger than 1. And that's why we see the current will keep increasing, because of the beta of these two parasitic BJT is larger than 1. So now we can understand the condition for latch-up can be seen. The first one, we need to have the current triggering, right? So this is how we understood from the thyristor, how we understood from a second control rectifier. We need to first in somehow give a little bit pulse current to trigger. So that's this one, current triggering. And second is the VPNPN is large enough. So that's the second one. So this is a condition in the end why we can have the latch-up events happening in our CMOS IC. So it must to satisfy these two conditions. That means if we want to sustain the latch-up, we want to make sure our latch-up is always continuous happening, then VCC should be larger than V hole, and ICC should be larger than I hole. And if that's the condition, and then our transistor will be always be in the latch-up conditions. This is also provide us another mindset that if we don't want the latch-up happening, that means we need to make sure that these two conditions won't happen. This provides us some strategy later on to prevent the ESD issues. So here is a short summary that from the different literature, but what they try to say is the same things. Of course, if you are pretty fresh in the ESD domain, if you try to look at this slide, you're probably being overwhelmed. You will be very scared because that's a pretty looks like pretty complicated. But I believe that if you follow the previous explanation, starting from the typical SCR and come to this moment, I think this is not difficult to understand. So how does it occur? For sure, as already said, the bias for VP and PM, it must be exceeding for the sustained voltage, Vs here. And also, injection of current by the triggering device. So we need to also make sure there's a current that can cause a electric event. So from the above consideration, the electric requires the following component. For example, a 4-layer structure, SCR. So that's why we are so care about this PNPN, parasitic couple, BJT. And we need to have the current injector. We also have need to have the pulse voltage that can trigger the electric event. And the important concept is that on the other hand, if we want to avoid the electric, we need to make sure our PNPN is smaller than sustaining voltage, which is this one. So this also gives us some consideration that if you want to qualify your product for the certain ESD standard, that means you must need to make sure your sustaining voltage can be higher in the environment that you can induce the ESD. So once the PNPN structure has a electric, the large current required by the above IV characteristics must be provided externally to sustain the electric. And to remove the electric, the current must be reduced below the holding current. So that means that if you can remove, you can make sure your current is below the holding current, then you can avoid the electric event. So that's also the important concept. So now all this understanding leading to the strategy that how we can prevent the electric. So first is for sure our operation voltage should always below our trigger voltage. That's for sure. That's what we understood. If this is larger than trigger voltage, then for sure this is trigger voltage here. So if larger than this one, for sure we will have the risk that device can be into the electric region. And if the device is, the electric is already happening, then we need to make sure our voltage is smaller than holding voltage and current is smaller than the holding current. That can prevent the electric event. So now we get to more practical to some of the example that happening in the real device level. So there's some also another strategy. That's this all the strategies mainly coming from what we understood the issue that we have been talking about, because we already know the electric is mainly because of the beta for our parasitic BJT. So if we can certainly reduce the beta 1 times the beta 2, that for sure can reduce the electric, the happening for the electric event. And also we can increase the substrate resistance or put some guard ring or separate the PNPN structure here, or we do some deep trench in silicon on insulator. The idea that why we can come up with this strategy is because the purpose is we want to separate the PNPN structure. So the reason now we know the ESD is because we have a parasitic coupling BJT. But if somehow we can disconnect this coupling BJT, then we can somehow to avoid the ESD. So this is purpose trying to disconnect couple BJTs. So for example, let's look at this one. The very interesting approach is, for example, this one with the SOI. So now you can see inside the SOI, it's not possible the BJT from this side can be coupled from this side because we have very deep change to isolate the signal and also the SOI to isolate the substrate. So therefore the BJT in here cannot be coupled with here. So that's one of the idea. And also the other two, just we won't talk in the very detail, but just for your understanding that in anyhow, if we can separate PNP by, we have additional N plus implant, P plus implant, or we do the guard ring, or we increase the substrate resistance. So the SOI is another example to increase the substrate resistance because the SOI is completely insulated, so you won't have the current flow. And then also the substrate resistance is the same. If we increase resistance, then we won't have the current flow. And this is a guard ring. So this is a guard ring. Guard ring is here. So now you can see if we have a guard ring protected inside, then this guard ring can avoid the nearby BJT coupled to this our original transistor. So now we understood what is actually the latch-up and why the latch-up is happening. So now we have to start to the next one is that how we can qualify our product in the different ESD capability. Because in anyhow, your customer, what they want is, for sure, you need to do some strategy to protect your device to avoid the ESD, but you need to prove that your product is being in the which kind of the ESD level. So in order to qualify your device, your product in the different ESD level, you need to have the ESD test model. So there are the three important ESD test model. The first one is what we call the human body model. That's what we call the HBM. So the ESD, as you already know, as long as we have the charge transfer, we can always cause the ESD. So the human body model is to describe the phenomenon between the human and also our IC. So this is a model to consider the ESD between the human and IC. And the second one is a machine model. The reason we have to consider machine model is because of in the real production line, your chip, your pack device, your IC is not picked up by human. It's always picked up by machine. You put your samples here, and the machine the machine arm will pick up the sample and put it in another place and transfer to the next process line or next place, and then the machine will pick up again and put another place. So then we have to consider that the charge in your machine arm can be also transferred to your IC as well. So that's why we call this as a machine model. So this is considering a machine or metal tool discharging through a device to the ground. So the second important model is what we call the machine model. And the last part is what we call the charge device model, CDM. So the charge device model is that the device itself might already have a certain electrical discharge. So you can see sometimes our IC has already the charge happening already. and then you try to put your IC contact in another metal surface, that can also cause the ESD event here. So you can see we have the discharge happening. And also this can cause a discharge. So therefore, that's why we need to also consider this case that we call the charge device model. So now we will one by one to explain. The first one is a human body model. So the human body model, we need to have a certain circuit to simulate the ESD event when a person charge either to the positive or negative potential touches an IC. So this is our typical testing circuit for our human body model. So the first one is we have the charge that will connect to here to charge our capacitance, and then we have the second part is this one will be connected, and then the capacitor will discharge here, and this is a DUT is a device under the test here. So the typical HBM classification level range between 250 volt up to 8,000 volts here, and usually we use a 100 picofarad capacitance charge with a high voltage and discharge to our IC here. And this is example also shown here. So first one, we supply 2,000 volt, either positive, negative, and charge into the capacitance. Then later, once the capacitor being charged, will start to discharge here to our IC, and with the different pins. So as you know, once we package it, we have so many pins, and these pins, each pin to pin, need to be verified by the ESD event. So we need to test pin to pin. And here is some of the standards. Here you can see the standard here. We have the military standard, we have the EOS ESD Association standards, we also have the JEDEC standards here. And the typical HBM waveform is shown like here. So that's a human body model. And next one is a machine model. So the machine model already said the machine model is trying to simulate the ESD event that the machine discharge through a device to ground. So it's mainly to simulate that the machine, between the machine and our IC. And the machine model is range between 50 volt to 400 volt here. And this is typical machine model waveform. And the standard is shown here. So here is some more detail. As a SAM, we first to apply the 200 volt and charge into our capacitance. Then we start to discharge to our IC for the different pins, and approximately 200 volt machine model is equal to 2,000 volt human body model. And the third one is a charge device model. So the charge device model simulates the ESD event when a device charged to a certain potential and then gets to contact with a conduction surface at a different potential. And the charge device model is ranged between 200 volt to 1,000 volt here. And this is some typical waveform for the charge device model waveform. So now, if your product has been tested for the HBM, CDM, or MM, and then you can start to qualify your product in a certain level. For example, for HBM, I think the lots of the customer at least want that your device can sustain for 2000 volt. So I think 2000 volt is a pretty basic standard for the product. That's also is a requirement that your product need to make sure to qualify in the HBM. That's called class 2 level. So if you look at the data sheet for if you try to purchase the IC component in the mouse or ditch keys, so if you have been working in the PCB design or try to soldering, try to buy some gate driver and so on, you can look at the mouse and digit key. And usually in the mouse digit key, they provide the data sheet from the company. And usually the data sheet will include information for their ESD capability. That's exactly shown here. They will clearly specify that their product has been already tested for under certain model and what's their capability. It will be clearly shown in the data sheet. So now if we try to compare all the three different models, so we have a CDM, we have a MM, we have a HBM. So we can see the peak current in the CDM model is higher. In here, this is CDM. CDM can cause very high current, and also the CDM is much faster here. So the similar rising time and total duration between the HBM and NM, so that can cause a very similar failure mechanism because of the timing, the total duration are the same. And the failure signal and discharge process of NM test are generally the same as that of HBM test. Therefore, the HBM test could guarantee the MM ESD robustness. So that means if you test HBM, if your HBM results good, then you don't have to worry about MM because the failure mechanisms are more or less the same. And usually the stress level for MM is approximately 10 times lower than the HBM. This is just an empirical experience. The protection voltage level for HBM typically 2000 volt. This is why in the previous slide I have mentioned that usually the customer at least they want for 2000 volt, while for MM is for 200 volt and CDM is for 500 volts here. And CDM is completely different from HBM and NM, and there's no correlation. And reason why it's completely different because the waveform is different. This is a CDM, this is MM, but this is MM, this is HBM. But if you look at the CDM, it goes very fast and very high in the beginning, and then it will be decreased also very fast. So that means the degradation mechanism for CDM must be different compared to the NM and HBM here. And so the CDM waveform corresponding to the very shortest ESD event and has a high rising time with a total duration only 2 nanoseconds. So this is some more like the correlation between the HBM and NM. So it's around between the 7 to 12.5, but I would say it's pretty depends on the technology. It's difficult to precisely quantify the correlation between the HBM and NM. So this is just for your reference. So then in the next one is we will do the system level ESD protection. So in the case of system level, that means that the ESD issue is not only happening in the device, but also in the board level and also the circuit level here. So, and then we usually need to have the spatial the designs that try to avoid the ESD can happening in the core IC. So in this case, you can look at this is our core IC. This is IC that provide as a main function. But for the ESD protection, we will have this ESD clamp that's externally connected. The idea is that once there's a huge current ESD event or huge voltage ESD event happening, this additional ESD clamp can start to help the current being discharged away. So if the current is already discharged through the ESD clamp, that means in our core IC, there's no damage because all the ESD voltage, ESD current has been already leaked away, so we don't have to worry about that. So this is the idea how we do the ESD protection in the system level. So in the optimized system, the largest amount of current is discharged by the ESD clamp, and only a small current reach the IC. But then we don't have to worry because the small current will not cause a huge damage. And in lots of cases, we use a diode. Diode is also one of the very basic, but it's also important for the ESD clamping here. So this is the idea for the system level, and we can consider this is internal, and we can have the external. So in the real product IC, we actually will inside internal, we also have the ESD protection inside our core IC. But the problem is that the capability for ESD internal protection is not good enough. So we also have to this external protection here. And but of course, then you can realize that if you want to minimize the ESD damage, you can put as many as the ESD clamping circuit around of your core IC as possible as you can. But one of the issues is the cost issue because it wastes the chip area. This is our area. But now if we put lots of ESD clamping protection nearby, the problem is that we waste a lot of area and then the cost is very high. So now it's in the end become the issue that how we can design the ESD clamping circuit versus the area efficiency. So we don't want that so many, we only want the several, but that's good enough. Okay, so we probably will take a 10 minutes break and we'll come back later.
它这个阿萨本应该不是这种，它阿萨本表示我不确定这边阿萨本跟那边阿萨本一样，但它的概念比较像是就像 SOI 一样，就是你要让这边的电这边增加，所以这样这样的话这边就不会插混在一起。对，所以我不确定这边的阿萨本跟刚刚讲的阿萨本。
可是这句话不是上述，而且是
对
这句话的也很奇怪，他说他增加阿萨本方式是把多频的能力加大。可是拉到的方式下降。你想，如果真的
看一下啊。哦，确实有点变小。没有，应该
如果它是马上不会增加，还是更不会减少，它反而是减少。
但是你这边的电流会变少。
这边电流变少，我就是
对
不会内圈。
对啊，所以重点就是要不会内圈。对啊，高度不会。对，所以它的 idea 其实是要避免这边 connecting， 所以这个想法跟这个 SOI 一样，SOI 你是不会有电流流出去。对。但是确实你讲这个是没错，我觉得这个叙述不对，因为你增加动力 concentration 应该是会降低的。对。但是我还是觉得增加 alpha 是没错，因为增加 alpha 就是让你这边的电流，这边也是一样，这边都把它 disconnecting， 有没有这个跟这个连在一起？这边 disconnecting， 这边这一块，对你这边就是你的 base current 去跟上去了嘛？对，所以你这边 current 变小，你就不会看到这个。所以我觉得它的 alpha 是指这边，你讲的是其实是已经是这边。刚有个，刚有个电路图上面有alpha的，
这个吗？
啊，对，但是它的 alpha 应该也会影响到这边的电流，所以不只是这边，包括这边，这整边的alpha，这整个都是alpha。对，所以你要把这边也要有一个组织放上去，所以这边的组增加的话，它可能这样电流变少，所以这边就不会冷场。
而且是如果我这边有alpha变小，我整个这样走这边这个也不会变小，我电流这样走，电流这样抽出来，这边也是
对，不会通啊，所以不会小。
虽然可是往上电流是对的，如果我
对啊，要增加你就流过来电流变少。
可是我
就是你这边对啊，有比这个。
应该是另外一颗 BJT 就不会看。
对，其实它这个 alpha 其实包含这边有啊。
这个不是
这边有个 alpha， 是对，这边有个 alpha， 所以你这边的 alpha 增加的话，你这个电流下来创到这边来，
量就不够。
对，它就不用打开。主要是这一颗的电流。对。
应该说不论是穿在这或穿在这都没关系。就你这边阻力上升的话，你这边下来的电流应该还是会变少。只要电流变少，你应该就控不太到这一颗然后你就没有办法让这一个路形成。
对。
这我这边快要这一边电流上去了，这一段快要大，这段快要大，那我因为我 BD 偏广中间这样子，这边电流大，边快要大，这个就是会控制。
没有，你就两个分贝，或者你知道分贝，就是因为你这边的组织够大的话，你额外电流很小，对。主要还是看这个电。
所以那个掺杂的可以，然后
应该是要减少完，应该是要比会少，对，才会拿到。对。
那另外我还想问之前老师上课有教过，就是说这个是Y 轴是 MTTF， 然后X轴是太阳，然后我会导时间去看，然后去量测，然后去看电流。因为我好奇是，那我们量测是指说，比如说我1完之后降回室温量，还是我一直 keep 在那个温度？因为不同温度下的量测，
通常是在那温度。
可是不同温度下的话，比如说以全身式来说，它的 IDVG 可能就会有不一样。
通常会 keep 在那温度量上面，所以你降温的时候慢慢降，所以你的电就会改变。所以通常就是你高温 straight 就是高温。
可是像你的 IDVG，比如说高温的 IDVG，
可是高温 IDVG 很难。对啊。
所以我就说这样子比较的话，他们不是就会定义，比如说你 drop 到多少？
对啊，就是每个每个电压会有不一样的。
因为不是有时候有什么样的就是有个加热，
没错，对，所以说你看你的
它不会到。那另外还有一个问题是跟老师课说的那个，就是machine 的 MM 的这个它那个 waveform 是怎么计算？
他就说你用这个方法做出来的话，它的产生 waveform， 它 casting 的 waveform 会长这样。对。
可是那这个跟 human 的不是一样的？
详细没有还行啊，就会有听不到，没有因为它这个要电感，对，你看这边是有高温加电感，然后这边只有电阻。
这个就是
这个就是模拟，就主要说是模拟 machine 造成的 ESD。
对，没错。
只是因为刚好他们的量不是很多，所以就是这个可以。
对。
好，感谢哦。
那个下标报告，然后我寄信2次给这个邮寄，然后他也是没有回，所以目前找不到这个。然后
真的，
这个他是然后这个还有对，对，真的对，不然的话就那这样的话就是说3个12分，对，好，我刚刚点名确认一下，对，就他从来都，我可能要确认一下，我看到交作业，他可能在办之后就会的，这个系统，好，下一块，对。所以如果说真的还是这个金属 hand 的 melting 的话，那我觉得是真的是比较相关，因为正常的 by 是操作就是1伏2伏，电流波才对几安培，对这种看的话不会造成这种生物就是对。
那第二个问题是，这特殊可能怎么判断它有到达2000伏的 spec？
这个可能你要看它就是2000伏的 spec 是长这样的，对，所以就是说应该是说它的意思是说，我今天2000伏的 HBN 档现在是这样子，如果它 pass 就代表2000伏的 HBN， 所以它不是用这个 curve 来判断是2000伏，就是说这是一个 example 2000伏的 HBN 是长这样，对，所以如果2000伏 HBN 打完到200-300 nanoseconds 都没有 fail， 就代表最 pass。
OK， 我觉得是看这个。
对。
Okay, I want to make the fix some errors here. So I think the increase substrates by decreasing the doping concentration. And the reason I think that why the increased substrate can also avoid the latch up is because if you look at this circuit diagram here. So once we increase the substrate resistance here, so you can actually reduce the current flow in here and also reduce the current flow here. So that means if you consider the substrate also resistant here, so if we have the higher resistance substrate, that means the current flow in this region is reduced. So if the current is reduced, then that means we have less current to trigger this BJT. So that's why I think that the increased substrate resistance can help to prevent the latch up. So the current in here is smaller. So we can prevent the latch up event. Okay, now we will introduce the transmission line posing. The reason we have to conduct the transmission line posing is that if you look at the setup for the human body model, for the machine model, for the CDM model, you need a very dedicated testing the tester for the ESD tester here. It's not easy to use those testers, especially in the on-wafer device. For the pack device, you can use those ESD testers to test the pin-to-pin. But if you try to understand the on-wafer ESD capability, it's not possible to use those ESD testers. So that's why we come up with this transmission line posing. And then the ideal transmission line posing is like if you look at the human body model, the waveform is like this way. And based on what we understood, the most damaged part should be always in the time that has a high current and happen in a very fast duration. So therefore, if we can generate the waveform, something like this one, we believe we can also induce the same phenomenon like the human body model. And similar, we can also use the transmission line posing to reproduce the degradation, the testing happen under the CDM model. So as we already mentioned, the CDM model has a waveform, something like this one, and it's happening in the very fast, usually down to the several nanoseconds. So if we can use the TOP to have the waveform like in this, then we can also use this waveform to understand the CDM model ESD capability. And this is VF is what we call the very fast. Very fast TOP. So the TOP is very efficient for the ESD characterization, and it has a stable, consistent pulse and very high current, and also for the short duration. That's why later on the TOP become one of the most widely used to characterize the ESD capability. So here is some more detail related to this transmission line posing. And we use several transmission lines to generate stable, consistent pulse for high current, short duration here. And in here, we won't talk too much the detail for the setup, but just let you know the concept. So we use a transmission line to generate the waveform here, and then depends on your voltage and current. In the end, you can start to generate the IV curve on our device under the testing here. So the idea is that we gradually to increase the different pulse voltage here, and then each pulse voltage will record for the current, and until a certain moment we start to see. So this is a current in the device, and this is a voltage in the device. So we can use this graph, start to look at the ESD, the latch-up event here. And then once we has this observed, that means we have the failure criteria met. So that means we start to see the device has a ESD induced values here. So this is a relation between TLP pulse and device leakage current. So this is a device leakage current. So unlike ESD waveform, the pulse from transmission line are simple and easy to use to diagnose the circuit or device operation. So in practice, transmission line charged to high voltage and then discharge into device being analyzed. And simulated ESD events are provided by discharge of the charging capacitance, which results in a very complicated waveform. So the information received from using TLP is compatible for those capacitance discharge of actual ESD event. So if you try to use a typical, this is a typical using the charge capacitance. For example, for the human body model, HBM, NN, or CDN here. We mainly use the capacitance to charge and discharge, but the waveform is very complicated. So we believe using the transmission line actually is much simple, but also is very useful. So here is the slide for the concept that we have the ESD clamp to protect our device. So a good ESD protection should trigger under low ESD current and be able to clamp the voltage of the protect IC at the clamping voltage here. So now the concept is that if you look at the original device, for sure we want to this device avoid the latch-up event. But if we look at for the ESD clamping device, we want this device can be into the latch-up event as early as possible, because then this can help us to have the current leak away from this ESD clamping device. So for the protection, for the main device, for the main protect device, we want to avoid the latch-up. But for ESD clamping, we actually want the latch-up happen earlier. Because once you have the ESD event, if you have the ESD event happening, discharge. So if we have the ESD discharge here, if the ESD clamping can operate before our protected device, so that means the current can be flow away through the ESD clamping and without being inside into our protect device. So that's the idea. So that's why we want the latch-up happen earlier in our ESD clamping. So this is the concept that a little bit different compared to our protect device. In our protect device, we always hope that we don't want the ESD, we don't want the latch up. But in the clamping device, we want the ESD happen earlier. So this is the example of the best case. So you can see, this is our protected device, and this is our ESD clamping device. So basically, we want to make sure this clamping device is entering the latch up operation earlier than the protecting device. Then we can make sure the current will flow through the ESD clamping, because now we have very low impedance. As you remember, once the latch up is happening, we have very low impedance between the power VDD to the ground. So that means all the current will go through in here and without entering into our protect IC. So that's the idea here. So we hope the latch up in ESD clamping is happening earlier than protected device. So these are the 4 different cases, and you can look up, but I would say the best is this one, because the ESD clamping device is first entered to the latch up, then our protected device. So that's why say the good ESD protection should be triggered under the low ESD current and be able to clamp the voltage of the protective IC at the clamp voltage which is lower than the breakdown voltage. So now if we comparison with the current waveform here, so by short pulses, self-heating in the device is limited, so we don't have to worry about self-heating effect. And the IV characteristic can be measured to much higher current level that's realistic for real ESD discharge. The information using TOP is compatible to low capacitance discharge. So this is one of the example. This is this is human body model. This is HBN. And this is a TOP with a different current. This is a TOP for 60 amp, TOP for 8 amp, and TOP for 4 amp. So now if we look at for the how to do the testing for the ESD, then we have to also consider the device under the test, the situation, the status for our device here. So here is the example. We first to do if we look at this is a package device, so we have to do the IO pin to power pin. For example, do the positive for this one. We ground it for the 1 pin, and we apply ESD for the 1 pin. So this is the positive. And also we can, this is a P to the ground. And also this is a P to the VDD. So we consider the ESD between this and this. We try to test the ESD capability between these 2 pins, or here ESD. So that's how we realistic to do the ESD testing. So you have to test all the pin to pin to make sure that your package device can sustain for the good ESD capability. Also, not only for the positive, but we also do the negative test as well. So it depends on your ground pin. Your ground pin can be the VDD or VSS. So that's one scenario, but also we can consider the stress pin is input output and the ground pin is another input output. So in here we mainly to consider the ground pin is VDD or VSS, but also we need to consider the ground pin is another IO, which is, for example, this is ground pin, this is our stress ESD pin. So we need to also ground this one to test, or this is a positive and negative. And this is another, is we stress VDD and we grounded another VSS. So we stress in here and we grounded in here. So that's another cases. So this is a very similar for the transmission line, but we just sometimes use another name called a square pulse testing. And this is a test we do on the pin, stress a pin, but only one pin at that moment to look at for the ESD stability. And also, if you look at for the case with the CDM, then we can also use the CDM testing in our package device. So we charge on the substrate. So we charge here. And then we discharge on any pin. So we charge at this place. And we discharge here. And when we talk about the protections, that's we already talk about for ESD clamping here. So that's this is also in the case of ESD clamping, we have the different possibility protection. And the first one is what we call using the TVS dial. So TVS dial, the full name is the transient voltage suppressor dial. So this is a dial that has an operation like in this way. So we have a forward conduction, we have a reverse conduction, and this is a case we the device being used for the typical dial, but for the ESD, we actually hold the device is operation in here and here during the ESD event happening. So the idea is that if we can operate in this region, then once this is here, once either we have the positive, this is positive ESD testing, or negative, so then if the device can be operated in this high current region, that means the current can be flow away from this TSV dial. And then, so the current, the idea is that we have this such transient voltage, but because of this clamping, so that's leading to the voltage inside our protected device is lower. So original, we have this transient voltage here, but a part of the voltage will be clamping by this TSV dial, and then the voltage really entering inside our protected device is much lower. So that's the idea. So the important feature for TVS is first, it's a diode-based protection with a low breakdown voltage, and we have a low clamping voltage, and that provides a low resistance path. And also it's a fast response time, and usually it's happening in the several nanoseconds. And we have a bipolar protection, so we can use to provide for the positive negative. So either this region can be operated, or either this region can be operated. So that's we call this as a bipolar protection. And then high inrush current handling, so that's a good. This is once the diode is operating on state. But once the diode is operating off state with a low lead current, this minimizes the impact during normal operation. And we have a low capacitance and also the small footprint. So that's one of the examples how we do the ESD protections. So if you look at the overall ESD protection strategies, this is our transistor. So we can find out that, as I say, the most weak part is always the outside. So we will place the last of the ESD protection from the gate side. So this is the ESD try to protect the gate region. So once you have the ESD event here, first of all, in terms of a system, first outside the system, you have one ESD. So then this ESD event happening, so you have a current flow away from here. But this cannot eliminate 100% of the current. So you still have a certain ESD voltage will be entering into our IC packaging. So this is a system. This is packaging. So still will be certain voltage enter into the IC packaging. So we need to start to do certain additional ESD protection. For example, we place the ESD clamping here, then we can make sure the voltage and then the current can flow away. But still, the part of the can be inside into our core chip, which is mainly related to our CMOS transistor. But now we still need to have another ESD and also the ESD to make sure that the stress, voltage, and current won't damage our outside. So this is the completely network for the ESD protection strategy. So in overall, the ESD protection is very complicated because we need to make sure that the weak part here won't be damaged by the high current, high voltage event. So that's why we need to place the lots of ESD protection. Here is a nearby our core IC. Here is for the packaging. Here is for the system. So a protection network must be device which will allow ESD current to pass through the IC without causing any damage to either protection network itself or the remainder for the IC. And we will shun the current away from the sensitive circuit. So the sensitive circuit is definitely here. So we'll try to do something to shun the current away, and we can prevent the high voltage across the sensitive circuit. So if you look at the protection device, we have several protection device, but ideally is that we want to have the high current capability because we want to have the current shunt away from this protection device, and low resistance, also small footprints because we want to save the chip area, and also we want to have a low parasitic that can avoid the loss of the operations, and the device is off. During the normal operation, the device will be only on once the ESD event is happening, and it's turned on quickly during the ESD here. So commonly used is we have the typical diode, as already said. Another one is what we call the ground gate NMOS. That's we generally call the GG NMOS. Or we have a second control rectifier. That's also the one very commonly used. So this is the one that I already mentioned, that how the protection device, like the diode, how we can use the diode to as a ESD protection. So the main, as I say, that in the normal operation, is always operate in this region if there's no ESD event, so that this additional protection device won't influence the regular operation. But once there is the ESD event, ESD strike happening, so the diode will be operate either here to here. So we want to have a high current, low resistance to shunt away the current. So ESD protection diodes are connected in the reverse direction, as shown here. They connected in the reverse direction, so they do not conduct the current when the voltage across the ESD protection diode. So that's typically it didn't operate. It only operated until we have the ESD strike happening. And we have the two kind of, one is unidirectional and another one is we put the bidirectional. The two diodes will be placed in series with each other. So both unidirectional and bidirectional can be used the idea is just to absorb the positive and negative ESD pulses. Then our device under the test won't be damaged. So the idea is the same. Once we have ESD event, but then we can use this ESD protection device to shunt away our signal, and therefore our device here won't be any damage. So this is an example that we have the dual diode ESD protection here. So we place the two diodes here. So the dual diode based ESD protection is a base non-ESD protection concept for the analog circuit here. So ESD dual diode typically consists two diodes connected in parallel, and under normal conditions, the diodes are reverse biased, so they don't conduct the current. But as the voltage exceeded a certain threshold, for example, breakdown of the diodes here, the diodes start to conducting, provide low impedance path for ESD current to flow. So that means once we have the ESD strike, this diode will be operate in the breakdown mode. And once it operate breakdown mode, we have the current can be flow in here and the end flow out. So therefore we can make sure that our CMOS won't be damaged by this ESD strike. So even nowadays, the dual diode is still very popular use in the lots of product. If you try to look at the ESD protection for the current product, they still use the diode for this back-to-back diode because of this is very simple design, and then that's very efficient with these dual diodes. And also, sometimes because of the gate oxide is very sensitive during the ESD stress, because as we already know, the gate oxide always suffers the lower voltage that can cause a breakdown. So usually we will have to consider the primary ESD or secondary ESD. That's because we want to make sure that there's no ESD strike will close to our gate side. So this is an example. As already said, we use a diode to shunt the signal away here. But then we place another secondary ESD to make sure that the signal here will pass through to the ground, and therefore our gate here can be well protected. So ESD stress applied will first turn on locally secondary protection, that's a green current path. This secondary protection current need to be lower than the failure voltage of a current. And also the higher voltage at the input pad will then trigger the primary protection. But the idea is very similar. We just try to place as many as a protection and make sure that our ESD strike won't damage our gate outside. So here is another example related to the MOS-based protection claim here that in the previous we use a diode and now we use a ground gate MOS. So the ground gate MOS is similar that try to make sure that we actually ground here. So the source and substrate shunt resistance control the trigger current necessary for forward bias of this region and then force the device into a snapback. So the idea is that once we operate, once we have this GGM MOS here, then we will try to make sure that the device can turn on in the parasitic NPN BJT. And once we turn on in the parasitic NPN BJT, then this GGM MOS operate in the electron mode. And once in operate electron mode, they can very efficient to shunt the current away. Okay, I was trying to finish the class today. So we have around 10 slides, so we save the 10 slides to the next week. So next week we have a group presentation. And by the way, just want to make sure that because I heard about there's a group who cannot always find one of their partners. So I'm just wondering, this guy is still with us or he already dropped. Liu Jihuang. Okay, it's fine. Okay, so see you guys next week.